Chapter 18, Heat and the First Law. Heat is energy transferred by conduction, radiation, or friction, not matter transfer. So for example, convection is, technically speaking, not a heat transfer mechanism. Let's start by talking about temperature. There are three common temperature scales: Kelvin, Celsius, and Fahrenheit. We will, in this course, very seldomly use Fahrenheit. Take a close look at the Kelvin versus Celsius temperature scales. Two key terms you want to look at right now are absolute zero and the triple point of water. Here's a really great demonstration video showing the triple point of water. Check out this 10-minute PBS video that talks about absolute cold. Notice the distance between the tick marks on the Kelvin scale are exactly the same as the distance between the tick marks on the Celsius scale. This is a great statement right here. 1 Celsius degree equals 1 Kelvin, but 1 degree Celsius does not equal 1 Kelvin. Make sure that makes sense to you. We're going to start by talking about the absorption of heat by solids and liquids. We'll then get to the absorption or production of heat by gases. Here's the qualitative description of specific heat capacity as well as the analytical definition. Make sure as you write this stuff down, you're really absorbing what it's telling you. In other words, learn as you transcribe. Here's a great bullet. Think of C, which stands for specific heat capacity, as temperature stubbornness. Box 2, Q equals MC times the quantity T final minus T initial, or more to the point, Q equals MC delta T, because delta T equals T final minus T initial. This is a key equation, which is why it's highlighted. Here's a table of specific heat capacities taken from your textbook. You have access to this yourself via Wiley+. Right now, let's just focus on the middle column that gives specific heat capacities in terms of joules per kilogram per Kelvin. Note that I could also express this as a joule per kilogram Celsius degree. This is highlighting the point once again that a Celsius degree is equivalent to a Kelvin. What is this saying about lead? It's saying that if I have 1 kilogram of lead, I need to add 1 joule of heat energy to increase lead's temperature by 1 Kelvin or 1 Celsius degree. Conversely, it's saying I need to remove 1 joule of heat energy from 1 kilogram of lead to reduce its temperature by 1 Kelvin or 1 Celsius degree. Now go all the way to the bottom and look at water. Water is special for a lot of reasons, including its very high specific heat capacity. Compare this number to lead. If I have 1 kilogram of water, I need to add 4,187 joules of heat energy to increase water's temperature by 1 Celsius degree or 1 Kelvin. Similarly, I need to remove 4,187 joules of heat energy from 1 kilogram of water to reduce its temperature by 1 Kelvin or 1 Celsius degree. Let's talk units. Heat is a form of energy, so we know joules is a valid unit of measurement. It's also common to use calories as a unit of heat energy. Check out box 3. 1 calorie with a capital C is known as 1 food calorie, which is equivalent to 1,000 calories with a lowercase c. 1 calorie, again with a lowercase c, equals 4.184 joules. Sometimes you see this conversion as 4.184 or 4.186 or 4.187. Here's a nutrition label for a snack bar. It contains 193 calories. That's 193 calories with a capital C. So that's it for the absorption of heat by liquids and solids. Let's talk about what happens when a solid or liquid absorbs enough heat or loses enough heat to undergo a phase change. Everyone knows there are 3 states of matter: solid, liquid, and gas. Let me just use water for the example here, but know that this applies to any solid or any liquid. If I add enough heat energy to a given mass of water, it will transform from the liquid state to the gaseous state. Similarly, if I have a given mass of steam and I remove enough heat, the steam will transform from gas to liquid. The heat that's involved from a phase change between the liquid and gas states is referred to as the latent heat of vaporization. Again, this is true in general, not just for water. If I have a given mass of water and I remove enough heat, that water will phase change to the solid state. Similarly, if I have an ice cube and I add enough heat energy to that ice, it will phase change from the solid to liquid state. The heat energy that's involved during a phase change from solid to liquid or liquid to solid is known as the latent heat of fusion. Let's look at this graph in table 5. I'm starting with a 1 gram piece of ice starting at -30 degrees Celsius, and I'm adding enough heat so that it ends up as steam, which is a gas, at 120 degrees Celsius. Let's break this down into segments. Segment A, I'm adding heat to the ice and it's warming up. It's not phase changing changing yet, so every bit of heat I add elevates the temperature of this ice. I use Q equals mc delta T. I plug in my values for M. C, the specific heat capacity of ice, is found in a table or it's given to me. I never memorize data like that. My job is to understand concepts and solve problems. My final temperature is 0 degrees Celsius. My initial temperature is negative 30 degrees Celsius. So my change in temperature is 30 Celsius degrees, and not 30 degrees Celsius, 30 Celsius degrees. That's a key point. That's why Celsius degrees in the numerator cancels with Celsius degrees in the denominator. I continue to add heat at a constant rate, and finally, my 1 gram piece of ice attains a temperature of 0 degrees Celsius. My heat keeps flowing in, and I start to change phase. I start to melt or transform from solid to liquid. Segment B is a flatline segment because all of the heat I add serves to break the bonds and to change phase. None of it is used to elevate the temperature. Again, this latent heat of fusion value for water's fusion, which means changing phase from solid to liquid or from liquid to solid, is given in a table or I already have it at my disposal. During segment B, I have a mixture of ice and water, but sooner or later that ice completely transforms to water, and all of the ice's melted water starts to warm up because I'm adding heat at a constant rate. So for segment C, I'm once again using Q equals mc delta T. So notice the final and initial temperatures. Notice the care I'm taking in specifying Celsius degrees. And again, know that constants are given to you or you look them up in a data table somewhere. Follow the process for segment D and E. And finally, I add up all of these heat contributions and I learn that 3,110 joules of heat is needed to take a 1 gram piece of ice starting at negative 30 degrees Celsius and transforming it to steam at 120 degrees Celsius with various warming and phase change segments along the way. Before we move on, let's take a look at this table, which is found in your textbook, so make sure you're aware of that and use it. We've just been talking about latent heat of fusion and latent heat of vaporization for water, so this is the table you would refer to. Okay, this next section is where we really start thermodynamics. Check out this video clip from Warped Perception. He's a popular YouTuber who makes ultra high speed or ultra slow motion videos of common everyday things. In this clip, he shows the operation of a lawnmower engine. There's a lot of thermodynamic devices all around us: the human body, weather systems, air conditioners, refrigerators, and engines of all kinds and types. I'm showing this now because a lot of the derivations refer to a cylinder with a movable piston enclosing a working substance. In this case, it would be a gas-air mixture. Hopefully this gives you a useful reference point because we're going to talk about thermodynamics for the next few chapters.
We have this L-head Briggs & Stratton engine with a transparent head that we built a few months back. Good job, Maddie. Wow, it looks great.
Yes.
How old are you, Maddie?
2.
You're 2.
2.
2 years old. Thank you.
Your turn.
My turn? Okay, thank you. For an ultra high speed shoot that we were doing for vision research.
We're going to use this example a lot. A cylinder with a movable piston enclosing a working substance. The working substance could be air, a gas, or a mixture of 2 or more gases. It doesn't matter. The system in this case is the trapped working substance. Boxes 2 through 7 are based on the basic definition of work. So this is a great opportunity to refresh your familiarity with work. Again, really learn this stuff as you transcribe it. Everything should make sense. You might have to remove some rust, but this is all stuff you've learned before. In box number 8, it's really important to see why theta equals 180 degrees. For the integral expressed in box 7, theta is talking about the angle between the displacement vector and the force vector. In this case, the displacement vector is pointing downward in the negative y direction. The gas itself, or again, working substance, is exerting an upward force. Why? Because Newton's third law says if I'm pushing down on the working substance will push up on me. So box number 9 contains our latest and greatest version of the work integral, but we can still do more. We remember the definition of pressure is force per area. I do some rearranging in box 11. Box 12 is an updated version of box 9. Box 13, I do some more clever processing, and in box 14, I have yet another updated version of the work done by this gas. Finally, I have my result in box 15. I'm using this definite integral and specifying initial and final conditions to end up with the general expression for work done by a gas, which could be a positive value or a negative value. This is a major expression. These bullet points summarize critically important takeaways from this. The expression in box 15 is only useful if we have a function that is integratable. We know that if we have a pressure versus volume graph, the value of this integral equals the area under that graph, under the pressure function. This last bullet, heat may or may not be involved. In general, work and heat are path dependent. You might remember non-conservative and conservative work. Non-conservative work is done by a non-conservative force, which means path matters, as opposed to the work done by a conservative force where only the initial and final states matter. This is a very recurring theme in thermodynamics, the whole notion of conservative work and non-conservative work. Both of these have to be familiar to you. So go back through steps 1 through 15, make sure you understand everything about what they're saying. Ask questions if even a sliver of what you're reviewing doesn't make sense, and make sure you're really clear on these 4 bullet points that summarize key concepts. Take a look at this simulation. Think of it as a cylinder turned on its side. My working substance is a mix of heavy and light particles. They could be atoms or molecules or particles. If my piston expands, my working substance does positive work. That's because the force exerted on that piston, which is this left barrier, by the working substance is aimed leftward, and the displacement of the piston is also leftward. So we have a leftward oriented force acting through a leftward oriented displacement. That's positive work by the working substance, in this case, this gas mixture. If I move this piston to the right, the force acting on the piston from the working substance is still leftward, but the displacement is rightward, and that corresponds to negative work. I'll mention this right now as well. Look at all the crazy movement by these particles. They possess a combination of translational kinetic energies and rotational kinetic energies. They also possess some amount of electrostatic potential energy. If the working substance is dense enough, the particles, which again are gas atoms or molecules, will electrically interact with each other. The total amount of the kinetic energies and the potential energy is referred to as internal energy. Look what happens if my gas does positive work and if I remove some heat from my system. You can see the temperature is decreasing, the pressure is decreasing, and there just seems to be less violence going on with my working substance. It looks like my internal energy is lower here than it was when my working substance did negative work and maybe I added some heat as well. The first law of thermodynamics. The internal energy of your system depends on how much heat flows into or out of it, as well as how much work it does on the environment or how much the environment does work on it. Here's a thermally agitated molecule, a segment of protein alpha helix. It's exhibiting internal energy. The combination of its kinetic energies and potential energy account for its internal energy, which we write as capital letter E_INT. So a system's internal energy is the sum of its kinetic and potential energies. We need to carefully keep track of the amount of heat that flows into or out of a system and the amount of work done by the system or on the system. Let's look at 3 different examples examples to reinforce this point. A thermodynamic system could be an automotive engine, an air conditioner, a refrigerator, a weather system. In this case, though, just to be different, let's use the human body as our thermodynamic system. So you wake up in the morning, you eat some cereal, you metabolize that cereal and get 150 joules of heat energy as a result. You then walk up a flight of stairs and do 100 joules of work. The first law says that the change in your internal energy is Q minus W. So in this case, 150 joules minus 100 joules equals 50 joules. Your body has gained 50 joules of internal energy. Let's look at the middle case. It's a cold and really windy winter day. You run outside without wearing a jacket and you lose 150 joules of heat through radiation. 150 joules of heat radiates off your body and away into the atmosphere. You try to walk to the corner, but you're facing a really strong headwind. Even though you're trying to walk forward, the headwind is blowing you backwards because you're on an icy covered sidewalk. So in this situation, you've lost 50 joules of internal energy. Negative 150 joules of the heat energy that you lost minus 100 joules of work equals negative 50. Here's our third situation. You again wake up, eat some cereal, gain 150 joules of heat energy, and this time you walk a little bit higher up on your stairs and do 150 joules of work. In this case, you break even. There's no change in your body's internal energy because 150 minus 150 equals 0 joules. This is the first law of thermodynamics, which is really a statement of the conservation of energy. A lot of times you'll need to be working with calculus, so this is the differential form of the first law. It's basically keeping track of three types of energy: your internal energy, heat energy, and work. In one sense, it's straightforward, but you do have to really keep track of things carefully. For example, heat flowing into a system gets counted as a positive. Heat flowing out of a system gets counted as a negative. If the system does work on the environment, that gets counted as a positive. If the environment does work on the system, that gets counted as a negative. Let's take a look at these interpretation bullets, although I covered them basically already. The term state variable is really important. Internal energy is a state variable, which basically means it has no memory of how it got to the point where it's at. Or you could similarly say internal energy is path independent. Other state variables include pressure, volume, temperature, and entropy. Once again, a state variable is not at all linked to the steps or paths that produced it. This contrasts with heat and work. Heat and work are both path dependent. Think of it like this. Imagine you're dragging a box along a concrete floor. You need to move it from your kitchen to your living room. If you go straight from your kitchen to your living room, you're going to lose a certain amount of heat to friction. If you drag that box from your kitchen along a detour, say you go from your kitchen to your family room and then to your bedroom and then to the living room, that's a much longer path and you've generated a lot more heat due to friction. Here's a blank template representing the thermotable method. This gives you a tabulated way to keep track of thermodynamic variables. There's a lot of deep dives that illustrate how to use this table, so make sure you know what to do. On the exam, this won't be an option. You'll need to use a thermotable, so mastering it isn't really a luxury, it's a requirement. Time to introduce 6 thermodynamic processes. The first one is adiabatic. Adiabatic means heat can't flow. There are 2 ways an adiabatic process can happen. A process could happen so quickly no heat enters or leaves the system, or the system is completely insulated. Here's another slow motion video of a fire piston. This is showing an adiabatic process. It's also showing compression heating. The compression happens so quickly that the generated heat doesn't have a chance to escape. Check it out.
Hey!
Here's a 4-stroke internal combustion engine. Intake, compression, power stroke, and exhaust. Again, intake, compression, that spark causes an explosion. The explosion generates heat, and that heat causes the gas-air mixture, which is our working substance, to expand. The 2 adiabatic processes here are compression and expansion. Again, let me say that again. We have compression and expansion. Those two processes happen so quickly, heat does not have an opportunity to enter or escape the system. Here's the other way an adiabatic process could occur. The system could be completely insulated from the surroundings, as you see here. This is taken from your textbook. So whatever heat is generated in the system, it can't escape, and whatever heat might exist out of the system, it can't enter. So because the first law says the change in internal energy is Q minus W, and Q equals 0 because it's adiabatic, we have the change in internal energy is equal to negative work. Think this through. If the piston moves up, that's positive work because the force and the displacement are in the same direction. If the work is positive, the change in internal energy is negative, and that makes sense. No heat is entering or leaving the system, but the volume's expanding, so that gives the working substance more breathing room. Temperature decreases and the internal energy also decreases. Let's move on to the isochoric process. Isochoric means constant volume. Sometimes it's referred to as an isovolumetric process. So no matter what happens, everything can change except for the volume. The volume remains constant. Here's an example of an isochoric process, the pressure cooker. Heat can flow in or out of a pressure cooker. The pressure can increase or decrease. The temperature can increase or decrease, but the volume remains unchanged. If the volume doesn't change, it means no matter what the forces are, no work is accomplished. Once again, heat content, pressure, and temperature can all change, but the volume remains fixed. Let's go back to the 4-stroke Otto cycle, that's OTTO, internal combustion engine. 2 out of the 4 strokes are isochoric processes. When the gas-air mixture, again also known as the working substance, explodes, a tremendous amount of heat is produced, and you get a very rapid increase in pressure and temperature, but the volume remains constant because it happens so quickly. The second isochoric process happens at the end of the power stroke. The exhaust valve is opened, and you get a very rapid flowing of heat out of the system, which reduces pressure and temperature. Back to the first law, the change in internal energy is Q minus W. In this case, there is no work because if the volume doesn't change, it means nothing moves, and if nothing moves, it means the force does no work. There are forces, but no movement means no work. So this simplifies down to the change in internal energy equals Q. If heat is added, internal energy goes up. If heat is removed, internal energy goes down. It's that simple. Let's talk about closed cycle processes. Here's a pressure volume diagram, also known as a PV diagram, and it shows a closed thermodynamic process. I start at 1, go from 1 to 2, from 2 to 3, from 3 to 4, and then from 4 back to 1. I end up at the exact same state that I started out at. This could represent a lot of thermodynamic processes, not just an automotive engine. And if the cycle is closed, that means whatever work is done by the system is equivalent to the added heat. The adiabatic free expansion. You hear the term adiabatic and you know that means no heat is flowing into or out of the system. Let's look at this situation. I have 2 thermally insulated chambers that are connected by a pipe. There's a valve that you can open or close. The thermal insulation means it's going to be an adiabatic process because no heat is going to flow in or out. My working substance, in this case gas particles, reside entirely in the left chamber. When I open that valve, the gas expands from the left chamber and into the right chamber. As it does so, no work is done. For work to be done, a force must move an object. If the right chamber is a vacuum, there's nothing to push. If nothing moves, no work is done. Not only is no work done, but there's no heat flow into or out of the system, so the change in internal energy equals 0 for this process. So it's kind of non-intuitive. The pressure's changing, the volume's changing, but the temperature remains constant. If there's no change in internal energy, there can be no change in temperature. We'll visit that in depth in the next chapter. But that's it. Adiabatic free expansion means work equals 0, Q equals 0, change in internal energy equals 0, change in temperature equals 0, but there is a change in pressure and volume. The isobaric process. Iso means same, baric refers to pressure, so this is a constant pressure process. This simulation does a good job showing the isobaric process. The gas or working substance is trapped in a container that is adjustable. If I add heat, the temperature increases and the volume increases, but look at my pressure, it remains unchanged. If I remove heat, the temperature decreases and the volume decreases, and still my pressure remains constant. If I add material, some variables may change, but not pressure. Same if I remove material. Other things change, but pressure remains constant. Any attempt to change the pressure is defeated because, again, this is an adjustable container. Here's another example of an isobaric process. A pot of boiling water. The steam produced by the pot of boiling water stays at atmospheric pressure because it's not bounded by any container. As the steam expands, the volume increases and the temperature decreases, but the pressure remains constant. For an internal combustion engine, the intake process, which happens right now, and the exhaust process, which happens right now, are both isobaric processes because the system is exposed to the surrounding atmosphere. Last but not least, the isothermal process. Iso means same, thermal refers to temperature, so this is a constant temperature process. Let's look at the first law. The change in internal energy is Q minus W. If there's no change in temperature, there's no change in internal energy, so in this case, whatever heat is added to the system or removed from the system is equivalent to the work done by the system or on the system. One way to keep the temperature constant is through a thermal reservoir. Look at this representation. If I push the piston down, there's going to be a tendency for the working substance to heat up. Because the system is in contact with a thermal reservoir, any heat that's produced flows to the thermal reservoir. Conversely, if I raise the piston, there would be a tendency for things to cool down. In this case, heat flows from the thermal reservoir to keep the temperature constant. That's what a reservoir does. If there's an excess of something, the reservoir absorbs it. If there's a deficiency of something, the reservoir contributes to it. Let me conclude this discussion of thermodynamic processes by talking about the Stirling engine. This is a really clever engine that literally runs on air. Here's the idealized PV diagram. It looks perfect. There's an isothermal expansion followed by an isochoric reduction in pressure and temperature, followed by an isothermal contraction, and finished off by an isochoric increase in pressure and temperature. Here's a more realistic PV diagram for this Stirling engine. It looks quite a bit different, but these four processes are in there. Okay, 6 scenarios going from some initial state to some final state. I'm going to go over scenario 1 in detail and leave the rest to you. Remember, learn as you transcribe. Okay, scenario 1. My system, or working substance in this case, is starting off with some initial pressure, volume, and temperature. The piston rises, so I have a decrease in pressure and an increase in volume, as shown in this path going from state I to state F. So let's go through this entire row. The path is from state I to state F. The piston is rising. My volume is increasing. My pressure is decreasing. I don't know enough to say what the temperature is doing. The temperature might be decreasing or it might be remaining constant, but right now I don't know. The thermodynamic work done through this process is shown by the area under the graph. Again, fundamental theorem of calculus. And I also don't know if heat is flowing into the system or out of the system, or maybe there's no heat flow whatsoever. That's scenario 1. Make sure you understand everything you wrote down and move on to scenario number 2. I'm starting at the same initial state I and ending at the same final state F, but I'm making this trip via 2 separate processes. From state I to state A, that's an isobaric expansion. From state A to state F, that's an isochoric reduction in pressure and temperature. Notice the shaded area for scenario number 2 is a lot bigger than it is for scenario number 1. Going from state I to state F, according to this 2-step process, produces a lot more work, and maybe that's my goal. Maybe I want to design a device that produces as much work as possible. I know for a fact that heat has to be entering my system between state I and state A. The only way my volume could increase and my pressure remain constant is if I input heat. I know heat is leaving my system between state A and state F. The only way I could maintain volume and reduce pressure is to remove heat. So there's a lot to really learn from scenario number 2. Make sure you go over each and one of these details and ask for clarification if anything isn't making sense. We're looking at the 3 state variables, pressure, volume, and temperature, and the 2 path-dependent variables, heat and work. Scenario number 3 is the reverse of scenario number 2 in that I'm undergoing an isochoric reduction in pressure and temperature starting at state I, and then undergoing an isobaric expansion to end up at the same final state F. Notice though, in this scenario, I'm doing a lot less work than I did in scenario number 2. Scenario number 4 is making the point that you can design a pathway from some initial state to some final state to meet meet specific goals. Maybe your goal is to produce as much work as possible, or maybe it's to require as little heat as possible, or something else. In scenario number 5, we're going from some final state F back up to some initial state I. You might look at the shaded area under this curve and say, well, that's a certain amount of work that's getting produced, but in reality, the work you see indicated here in this graph is negative work. When going from state F to state I, you can see my volume is decreasing. This means that although the pressure is trying to push in one direction, the actual displacement is in the exact opposite direction. That constitutes negative work. Scenario number 6 is illustrating a closed loop process. I start at initial state I and I end up at initial state I. You might think, well, if this is a closed loop system, my net amount of work is 0, but that's not true. Otherwise, engines would do no work for us. This graph shows the net work done. You can see going from state I to state F in the forward direction produces a lot of work, but going from state F back to state I produces a certain amount of negative work, and in this case, the total amount of positive work is greater than the total amount of negative work, and you're looking at the net work in this figure. Going from some initial state to some final state can happen in a number of different ways. If you really study these scenarios and really understand what's going on with pressure differences, volume differences, temperature differences, and heat flowing in and out of the system, as well as the net work done, you'll be in good shape. Here's the first of 2 really good summary tables. Make sure you really learn everything as you write it down. This is the thermodynamic process summary, and here's the Iris first law summary, named after the student who thought this up. If you think of any useful modifications or additions to these lecture notes, let me know.